Alright, so the first set of identities I'm going to talk to you about today are the angle addition and angle subtraction identities. And within the first 15 seconds of the video, I will tell you I don't have these memorized. To be honest, I don't use them often enough. The AP exam doesn't ask for these. They don't test them at all. On the IB exams, they test them, but they show up in a formula book. They give you a formula book during the exam, and you'll get to have these for your reference. So for the purposes of the next few years' worth of class, these are really not things that we need to have right in the forefront of our minds, for my classes anyway. If you're able to memorize them, if you're a memorization person, you can get these in your head, great. It just builds up a library of tools that you have. I personally have not ever been very amazing at memorizing things, so these have really just never made it into my mind. If I ever really need to find them, I sort of remember the structure of them, and I can sort of figure them out, but it takes me a while. So I'll briefly go through how they work, and then we'll get into some examples. So if you want to know the sine of, actually let's look at cosine because that has a more interesting sign in it. Suppose you want to know the cosine of one angle plus or minus some other angle. The idea is you can simply plug in your first angle for A, plug in your second angle for B, and then because this is plus or minus and this is minus or plus, it just means use the opposite sign. So if you're doing addition here, do subtraction here. If you're doing subtraction here, do addition here. If you run through this computation, it will tell you what the cosine of that addition or subtraction is. Right? So it's a really neat thing. It allows you to find the sine and the cosine of two angles which have been added together or subtracted from one another. So I have sort of two fairly simple examples in one. First, let's compute the sine of 75 degrees. Right? So in order to come up with what the sine of 75 degrees is, I'm going to have to come up with two angles that either add together to make 75 or subtract from one another to give me 75. Right? And it helps if they're like unit circle angles, in other words, angles that I know a lot about. Right? So personally, I'm going to go with making this the sine of 45 degrees plus 30 degrees. Okay. So now, if you remember your formulas from the previous page, we can find that the sine of 45 degrees plus 30 degrees will be equal to the sine of 45 degrees times the cosine of 30 degrees plus the cosine of 45 degrees times the sine of 30 degrees. Just barely fit that in there. So now I can go back and simplify this. Right? This is the square root of 2 over 2 times the square root of 3 over 2 plus the square root of 2 over 2 times 1/2. This is going to give me the square root of 6 over 4 plus the square root of 2 over 4. And so I end up with my value of the sine of 75 degrees. 75 degrees being the square root of 6 plus the square root of 2 over 4. And that's my answer. It's worth taking a moment to ask whether or not this makes sense. And the way I would encourage you to do that is think about what this value is. Can you approximate this value at all? Like, think for a minute. Like, what would you call the square root of 6? If it was me, I would call it, I don't know, like maybe 2.3, maybe. The square root of 2 is like maybe 1.4-ish divided by 4. That means I've got 3.7, in the neighborhood, 3.7 divided by 4. That means this is like a little bit less than, like just barely less than 1, which is perfect because that's exactly what we expect the sine of 75 degrees to be. If we pictured 75 degrees being sort of up here somewhere, that sine value seems to be almost 1. This answer seems reasonable. Okay, you should now pause the video, work through the cosine of 15 degrees. You're going to do the same thing. Find two angles that either add or subtract to give you 15 degrees, and then work through it. So what I'm going to use for this one, I assume you guys have tried this on your own, I'm going to use the cosine of 45 degrees minus 30 degrees, because that'll give me 15 degrees. Let's see here. So now I just have to sort of plug this into the formula and work through it. So the cosine formula goes cosine of 45 times cosine of 30, and then remember this is that interesting sign. Because this is a negative symbol, I'm going to end up with a plus here. And then on the other side of it, I'm going to end up with the sine of 45 degrees and the sine of 30 degrees. And I just, work these things out. Square root of 2 over 2 times the square root root of 3 over 2 plus the square root of 2 over 2 times 1/2. This is actually really entertaining. I wasn't expecting this. But it actually plays really nicely with other things we've talked about. When we simplify this, surprise, surprise, it actually ends up being the same value that we had before. I end up with the square root of 6 plus square root of 2 over 4. So it turns out we just found out also that the sine of 75 degrees is equal to the cosine of 15 degrees. Right? Is that surprising? No, actually. Again, if we think about our unit circle, 75 degrees is up here. We're looking for the height of that. 15 degrees is it's a very similar angle down here. Like this piece here and this piece here are the same. So it's not surprising that the sine of 75, the vertical part, and the cosine of 15, this horizontal part, would be the same as one another. Neat stuff. That was awesome, and I wasn't even expecting it. Let's get on to the last example that I have here. You guys are really probably thinking that I'm just trying to beat this idea into the ground, and maybe I am. I'm now effectively asking us to prove the same identity that we did in the previous video, where we sort of talked about the idea of the cosine of x minus pi over 2, or x minus 90 degrees being the same as sine. So take a minute and try this on your own. Use the angle subtraction or addition identity, and see if you can see what this does. So my thought here is that if we do literally the cosine of x minus pi over 2, then we can plug this into the subtraction cosine identity. I can find that this is going to be the cosine of x times the cosine of pi over 2 plus the sine of x times the sine of pi over 2. Note here that I use the opposite sign between these because I'm using the cosine formula. So let's see here. This gives me the cosine of x times the cosine of pi over 2, which is actually 0, plus the sine of x times the sine of pi over 2, which just so happens to be 1, which means we get 0 plus sine x. And sure enough, we conclude that the cosine of x minus pi over 2 is, once again, the sine of x. And I almost, I was about to draw a box around this, yay, I did it. Don't do that. They asked you to prove that. It's like saying, show this, and you're like, yay, I showed it. If you want to box anything, literally box everything. Which, in practice, means just don't box it. It's not necessary. You correctly did the work, you showed what you needed to show, and that's all we need to do. We don't actually need to put a box around the thing. So that's all I had in this video. I'll see you in the next one.